Hello students, welcome to lecture 22 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture will be discussing about periodic arrays of metallic wires. So here is the outline. We will continue from the rotted medium that we discussed. We will see how you can derive Drude model for periodic array of these metallic wires, and we will take an example of wire medium and discuss in details. So, the lecture basically starts with the discussion of rotted medium, which are made of nothing but thin metallic wires arranged periodically in vacuum or dielectric. So, 1D, 2D and 3D wire mesh networks were systematically studied by Rotman about half a century ago, right. So, these are the different type of structures. As you can see, a two-dimensional array is basically shown in this first figure. Okay, so this is a 2D wire array. So these are the axes x, y and z. So here you can see this is for z polarized electric field, that means the electric field is along the length of the wire. Okay, and then you have this second one, which is basically a 3D lattice, again for any electric field that is polarized within the yz plane. So you have added this third dimension by adding this wires here, and this is basically a kind of periodic cubic lattice. Okay, so this is basically when your metallic wires are basically forming a three-dimensional mesh. Okay, so the wire medium basically becomes quasi-isotropic, and it can exhibit a plasma resonance for field for any arbitrary polarization angle. So this is where the things become interesting in this case. However, this is also not bad. This is like, you know, you have you need to maintain the electric field to be polarized along the yz plane, okay, like this plane yz you can see here. So this artificial wire composites basically behave like dilute plasmas. Okay, so they basically can create negative electric response with some adjustable strength. So they were initially known in radio engineering as artificial dielectrics with tunable properties. This same concept was done long back, but then it was revived and it got popular in recent physics and metamaterial science when Sir John Pendry gave a broader relevance and application to these wire meshes that can be used for creating negative permittivity at a desired frequency range at will, and that can be clubbed with another metamaterial that can provide negative permittivity, negative permeability also at the same frequency, and then you can get a left-hand material or left-hand metamaterial, right. So this is the main purpose. The rotted medium could exhibit plasmonic behavior within a specific frequency band. So as you can see in this figure, if you consider this particular wire grid or wire mesh, you will see there are two important physical parameters. The first one is the diameter of the wires, that is 2r, and then another important parameter is the periodicity of this wire lattice, that is A. So the response, as you can see, will be completely dependent on these two important geometric parameters. The first one is wire diameter r, and the second one is unit cell length, that is the lattice constant A. So what you have to pay attention to is that the unit cell length, that is the lattice periodicity or A, should be way sub wavelength, that is much smaller than the wavelength of light, and that is when the wire array will behave as an electric metamaterial. Okay, so that is the case when electromagnetic radiation that will be falling on this material will not be able to, you know, resolve the wires, and rather it will see some effective medium. So the main objective here will be to derive this effective dielectric function, which can be written as epsilon of omega for this wire grid structure. So, for simplicity we will be considering this structure which has got only two important parameters A and 2R. Okay. So, as you can see, the composite medium is apparently anisotropic, and the polarization state that we will be interested in corresponds to a plane wave propagating in xy plane, okay, with its electric field polarized along z, that is along the length of the thin wires. Okay. So, you can understand that we are only interested in that particular dimension. So, epsilon permittivity or epsilon omega, okay, represents basically the epsilon zz omega, that is the zz component of the 3 by 3 permittivity tensor. So, in this particular scenario, the effective permittivity epsilon effective, okay, of this wire medium will follow a Drude like model. So, you can write epsilon effective as a function of omega as 1 minus omega p square divided by omega times omega plus I gamma. So, what is omega p here? That is the effective plasma frequency, and gamma is basically the effective damping constant. Now, unlike real Drude metal, okay, this omega p and gamma here are not intrinsic property of the material. They are basically depending on the wire array geometry and metal properties. So, this is where you are creating your own artificial material. Normally in any metal, these are kind of fixed natural properties, these are the intrinsic properties, but here they are not. Okay. So, here you can do everything by designing this wire array and change. Okay. So, the key goal here will be to estimate this omega p and gamma using these known quantities, and there are multiple models that exist for estimating this effective plasma frequency in such a rodded medium, but we will strictly follow the effective mass approach that was initiated by Sir John Penry in his seminal paper. So, in bulk metals, you will see that the plasma frequency basically depends on free electron density, the mass, and they are typically situated in the UV visible spectrum for the case of gold conductors, right. So, below the plasma frequency the material behaves like metal. So, the electromagnetic wave is reflected. Above the plasma frequency, it basically gives ways to the incident wave. So, the material becomes transparent, right. So, we will see that in such a wire medium the plasma frequency is much lower as compared to the normal metal, mainly because of the two factors here, that the effective electron density is basically getting diluted by a factor of pi r square divided by a square, because you assume that if you have a equivalent area of a square, here the only region within this a square that is having electron is basically the metallic wire, and the area of that will be pi r square. So, this is the factor that tells you that what is the effective electron density, and this is caused because of free electrons being confined within only the physical boundary of the wires. And the second one tells you about the increase in the effective electron mass. Okay. Now, this second factor was described by Sir John Penry, okay, and he described this effect of effective electron mass, okay, getting increased, that is resulting from the reduced or that is basically coming from the induced current in the wire and the excited magnetic field. So, the self inductance that is possessed in the metallic wires acts to oppose the rate of change in the current, which is basically a direct result of the Lenz's law that we all know. So, this is a conceptual context effect that is basically tied to this context of described self-inductance effect, not actual mass increase. So, you can think of increase in the effective electron mass, right. So, the modified equivalent plasma frequency accounts for these two factors. So, if you consider for the reduced effective electron density, you can consider the new density as n effective, which is n, and then you have this factor that was calculated here, pi r square divided by a square. And if you want to modify the plasma frequency further, considering the increase in the effective mass of the electrons that is coming from the self inductance, okay, you can also do that. This is done using the concept of generalized, which is the canonical momentum from quantum mechanics. So, you can calculate the total momentum P equals mv plus qa. So, here v is basically the charge velocity and a represents the vector potential, m is nothing but the static charge and q represents m is the static mass, sorry, and q is the charge, right. So, the effective mass you can obtain due to self inductance in the form of m effective, which is E a divided by v. Okay. So, for a mean velocity v and free electron density n in the metallic wires, the current that flows through one wire can be given as pi r square E n v, right. So, you can use Ampere's law to compute the magnetic field H r at a distance r from the wire center, and you can express this magnetic field H r equals pi r square E n v divided by 2 pi r, right. So, the magnetic field which is directed along the z axis in terms of the curl of a vector potential, right. So, you can write H r, which is coming from this vector potential, which is taking the curl of it. So, curl of A r divided by mu naught. Now, although you can although generally speaking the vector potential A r is not uniquely defined because of its issue of Gauss choices. So, you can make an assumption that your r is much smaller than A, and in that case due to lattice symmetry also you can consider A r, the vector potential, in this particular form, that you have mu naught r square E n v divided by 2 ln A by r. So, for good, I am not going into the details of this, you can look into the papers by Professor Pendry if you want the complete mathematical details for this. So, what I wanted to tell you that the vector potential is all dependent on the physical parameters A and r, and for good conductors we have seen that the electrons basically move on the wire surface. Okay. So, in that case it is safe to assume that all the electrons will basically experience the same vector field A r, right. So, substituting into the effective mass formula will give you m effective, which is basically mu naught r square E square n divided by 2 ln A by r. So, you can actually see what is the effective mass, right. So, once you know the effective mass, you can also compute the plasma frequency of this wire medium. Omega p square will be nothing but n effective E square divided by epsilon naught m effective, right. So, n effective you already know because of this factor how it will come down from n, and then you can also calculate substitute the value of m effective, okay, and this is what you got. So, you can see your plasma frequency is dependent on A and r. What is C naught square? That is nothing but C naught is basically the speed of light in vacuum. So, C naught is 1 over square root of mu naught epsilon naught. Okay. So, this is how you can calculate the plasma frequency of this wire medium, completely dependent on the two physical parameters A and r. Shalaev and Sarichev, okay, they also provided similar kind of an expression, okay, but they actually have gone for more complicated but precise derivation of this effective plasma frequency of this wire medium, okay, and you can see that this equation, although they are dependent on the same two parameters, it is more specific, okay. And even Maslowski et al., they also came up with an expression for plasma frequency, which is slightly different, but again similar kind of parameter dependence is there. You are just dependent on the two physical parameters A and R. So, if you compare between these two models, and you will see that all these approaches agree reasonably well with the transfer matrix simulation. Okay. So, the Shalaev and Sarychev expression as well as Maslowski improved model for plasma frequency, although they give you better prediction for the plasma behavior, okay. And to complete the Drude model for effective permittivity, you can determine the next important parameter, which is the effective damping constant, right. Now, damping constant gamma basically represents the loss factor in the wire medium. So, if you consider gamma equals 0, that means you are considering the wires to be perfect conductors. So, in that case you can write epsilon permittivity, epsilon effective omega to be 1 minus omega p square by omega square. So, gamma is basically 0, right. Now, in real metal you do not have gamma equals 0. So, you have a finite conductivity that is giving you some ohmic or resistive kind of losses. So, you have gamma which is non-zero. So, this is incorporated by introducing a imaginary part to the inductance, and you will see here how it is done. So, you consider the magnetic field, okay, HR, and for that the unit inductance L for a particular wire can be estimated as L equals mu naught integration over R to A by root pi HR dr divided by pi r square E and V. So, that gives you the inductance is typically equivalent to mu naught by 2 pi ln A by R. So, here you can see the denominator basically equals the current flow in the wire, and the integration upper limit, which is A by pi, basically represents the effective radius of the unit cell in this wire array, right. So, what is the validation limit for this particular expression? You will see that these are all valid for very thin wires where R is considered to be much smaller than A. Now, by comparing the plasma frequency expression with the inductance, you got this relationship that omega p square can be related to the inductance as 1 by epsilon naught A square L. Now, in this particular equation, you have a direct correlation between the wire inductance and the plasma frequency of this overall system. So, when the metal has a finite conductivity sigma, you can say that the inductance of the wire has got a complex value, and you can substitute L as L plus sigma pi r square by I omega. So, in that case you can, if you put that here, you can say that the effective permittivity of the wire medium in the Drude form will. So, the effective permittivity of the wire medium can now be expressed in a Drude form as epsilon effective equals 1 minus omega p square divided by omega times omega plus I epsilon naught A square omega p square divided by pi r square sigma. So, this is obtained by combining the expression for the effective permittivity. Okay. So, all these things you can put here, and you can obtain this effective permittivity of the wire medium in the Drude form, right. So, what we see here is that if the wire array is basically embedded in a host medium which has got a permittivity of epsilon h instead of vacuum, in that case the first term on the right side of the equation, this one, will get replaced by the host medium permittivity epsilon h. That is a very simple thing to do. So, you can actually consider this metallic wire array to be embedded in any other dielectric medium, and in that case this one will be replaced by epsilon h. Now, the effective plasma frequency omega p in a wire medium thus can be, we have seen that it can be derived via the medium's geometric parameter, that is A and R, and that basically allows you targeting specific frequency ranges from microwave all the way to optical frequencies. You can change the design of your wire array and you can put anywhere in between, right. So, by using thin wire arrays, the plasma frequency can be reduced by several orders of magnitude compared to bulk metal. So, that is also one big thing, because typically the plasma frequencies of the bulk metal, they lie in much higher frequency range. So, if you use this kind of thin metallic wires instead of solid metal, you can bring down the plasma frequency, and that allows you to make microwave metamaterials as well. Something like, for example, a wire medium with a plasma frequency in gigahertz range, that is something amazing. Okay. So, let us take an example here. So, if you consider a two dimensional wire array which has got a wire radius of say 5 micron and the lattice constant to be 40 millimeter. Okay. So, you see you are basically considering R is much smaller than A. So, if you consider the wire to be made of silver, which has got free electron density of N, that is equal to 5.8 into 10 to the power, I think that is 10 to the power 28 okay, meter cube per meter cube. So, okay, read it like that, just correct it. So, if you consider material, the wire is made of silver which has got free electron density N equals 5.8 into 10 to the power 28 per meter cube, and it has got conductivity of 6.3 into 10 to the power 7 Siemens per meter at room temperature. Now, you can see that because of this geometry, the electron density can be diluted by 8 orders of magnitude, and from the earlier equation that you have seen, that the effective electron mass will increase, and it is something like 2.1 into 10 to the minus 25 kg, which is basically heavier than a silver atom, right. So, with these two effects you can combine, and you will see that the plasma frequency is basically dropping by 6 orders of magnitude. So, how it is working? Because if you look into the expression given by Sir Pendry, omega p square depends on N effective E square divided by epsilon naught M effective. So, this is increasing, this is decreasing, both equivalently bringing it down. Okay. So, that is both bringing your plasma frequency down. So, you can see that you get omega p in the order of gigahertz. So, that is 2 pi into 1.0 gigahertz. Now, if you do not go with Professor Pendry's model, and if you try to solve it using the alternative models which we have already seen, that Shalev and Sarichev expression, which is this one, omega p square equals 2 pi c naught square divided by a square ln of a by root pi plus pi by 4 minus 3 by 2. So, and the other one was Maslovsky expression, that is given as omega p square equals 2 pi c naught square divided by a square ln a square by 4 pi into a minus r. So, in these two cases you get slightly different value. Okay, omega p will be 2 pi into 1.1 gigahertz. You see there is a slight variation, but more or less they give you the same order of magnitude. So, it tells you that you get plasma frequency which is way below the bulk metal plasma frequency. Okay. So, that is how you can make things work in the gigahertz range. You can do that. Okay. So, keep this in mind as well, because it will be important for our next lecture. So, we will stop here and we will continue with the periodic array of metallic wires in the next lecture. So, if you have got any query regarding this one, drop an email to this email address mentioning the course name and the lecture number and the subject line. Thank you.